right? How fast that they can go, and sometimes maybe the diffusion step, maybe the rate controlling step when you see a product leaving this surface. So really, it's quite a complex thing that we can involve. So each step, I think each step has its own desorption rate, and many only one step will control the overall reaction, and this is known as the rate determining step. Okay, and then a little bit of jargon when you talk about these reactions. I think a few things, and you can treat all of these in thermodynamics. We don't want to go into this. We just want to focus on the surface reaction step. And sometimes you hear this jargon when you read the literature, especially the catalysis people. They will say things like structural sensitivity. What does that mean? It means that the structure is sensitive to what kind of plane that you have, like whether you have 100 or 111. How perfect is your plane? You know, do you have a lot of step or defects? And in a particle sense, right? If you're looking at the particle size may have a lot of surface defect and so forth. Okay, so that is structure sensitive. Right? Conversely, if a structure is not sensitive, it just depends on the area. It's strict area consideration, because the more area you have, the more reaction rate that you expect, right? It does not depend on the detail of the structure, in other words. Whether you have 111 or 100 plane, it does not matter. It's just a surface area defect, okay? So in the later case, if you don't care about the detail of the surface, then you have structural insensitivity. If you do worry about those things, because certain planes are more reactive than the other. Why? Because those planes have more reactive site than other planes. So this will be structure sensitive. So for example, silicon 100 is more reactive than silicon 111. So in semiconductor industry, they use silicon 100 because that facilitates better reaction. It allows you to make transistor a lot easier because the surface is more reactive. You can promote different type of reactions. Second is the importance of chemi-absorption before the reaction, and two mechanisms that I really want you to remember for that is that when you're talking about bimolecular reaction, bimolecular means involving two reactants, you have two different scenarios. If you have a bimolecular reaction involving chemi-absorption of both reactants before the reaction, then you are following the so-called Lambert-Hinshelwood mechanism. In other words, the reactant has to stay on the surface first. Both reactants have to absorb first, and then reaction take place on the surface. The two reactants have to meet on the surface. Okay, as opposed to the Eli-Riedel mechanism, whereby you only need one of them on the surface. Okay, so in the Eli-Riedel mechanism is that one absorbate on the surface, and the other reactant can come from the gas phase. Okay, the second species can come directly to the gas phase and then react with what's on the surface. So slightly different, and sometimes when you read the literature, you will see this type of mechanism. Lambert-Hinshelwood versus Eli-Riedel mechanism, and you can study them. You know, you can see what's going on between both reactant on the surface versus one reactant on the surface. And to give some efficiency of a catalyst surface, for example, people often talk about this jargon, reaction rate, for example, is the number of product per catalysis area per unit time. Okay, and of course this is just like the reaction rate, desorption rate we talked about, is a rate reaction, right? So it's some sort of rate constant times some function, right? Some function of your concentration of pressure to some power. Okay, this power is of course the order of the reaction in the same way that we discussed before. And this rate constant follows the Arrhenius equation, and this is where the catalysis come in. The catalysis provide a different activation energy, E star activation energy, and therefore it speed up this constant. It changes. If this is small, you increase the rate constant because you have a negative in front here. So the Arrhenius equation tell you right away that you have this type of thing. This is kind of the activation energy for a lot of these little catalysts with high catalyst direction here. Then we have something called turnover number, which the catalysts will use quite a lot. That the turnover number is the number of product molecule formed per catalysis site per unit time. So when you talk to chemical engineering people, they would mention these turnover number. The higher turnover number, the more efficient the catalyst is. Okay. Next, they would talk about this sort of a reaction probability, right? Reaction probability related to turnover number. Is the ratio, right? Reaction probability RP is in fact turnover number divided by the rate of molecular collision. Okay, is the ratio of the number of product molecule to the total number of molecule striking the surface. So in other words, you have a flux coming into your catalyst, and you have turnover number. So the turnover, the amount of molecule produced per unit time divided by this flux is the reaction probability. Nothing more. And of course, in catalyst, you talk about active site. And active site is often the defect site. The defect site are King's and step services and so forth. And Gabor Samajai have contributed a lot of understanding about these active sites that you see. Usually, the most reactive sites are not on your terraces. Remember our terraces, TLK model, right? Usually, they occur at the last of the King's that you see here. Okay. So in the last bit of these terminology, what about catalyst? Right? Catalyst was invented by 1836, and he by the guy named Berzelius. The same guy, I believe he is the same guy who discovered silicon actually, and defined catalyst as substance that accelerate chemical reaction without changing itself. So a classic catalyst reaction is the Fischer-Tropsch reaction. Some of you may have heard about this in organic chemistry courses. And the Fischer-Tropsch reaction is important. It changed the economics of the world.